Okay, great. So, yep, I'm Tim. Good to be back in Queen Mary. So this is a joint piece of work with two of my colleagues, Youngjin and Yu, who are somewhere in the audience, hopefully. This piece of work is about some experience in an application we were working on to do with finance. And we pretty much discovered some horses and some of the state-of-the-art work in this area and perhaps succeeded in dehorsing it. So hopefully this is going to be interesting to you guys. Warning, you might have to learn some finance if you sit here in the audience, but I will try to make it as painless as possible to learn the minimum finance required to understand what was happening here. So, okay, option pricing. What does that even mean? So first of all, mini finance tutorial. What is an option? It's a contract that gives someone the right, but not the obligation, to buy an asset at a particular price, strike price in the jargon, at a particular future date, maturity date in the jargon. So this is perhaps best illustrated with an example. So at some particular time, for t equals 0 today, company's stock price is $100. And maybe we want to buy an option with a strike price of $110 for 5 days later. So if we have an option contract like that, what does it mean? It means that in 5 days, if the stock price is 120, we can execute the option, which will give us the right to buy it for 110, because that was the strike price, and then sell the stock immediately at the market price, which is 120, and then profit $10, right? So it's a contract that will let us do that if the price is 120, but if the price is now below 110, we would just not use the option at all, and then we won't have lost any money at all, right? So these are the kind of contracts we are talking about. And now the learning question here is, how much should this contract be sold at the beginning, time t equals 0? So the point is, because we don't know what the stock price will be in the future, we don't know exactly how to evaluate such a thing. And so what this stock price should be sold at will depend on various factors, like how long in the future is the maturity date, what is the current asset price, and so on. So the question is, how can we answer this question given all of those parameters of the option contract that we want to price? So a little bit of a contrast about how this problem was traditionally treated historically. Economists would observe these numbers like the price of the option and the various market factors like the maturity date and so on, and they would use their economic knowledge and come up with some assumptions like a stochastic process that relates these two and write down some more like a normative equation. This is how I think these things should relate. In contrast, machine learning guys come to this kind of problem and they say, oh, okay, so if there are some independent variables like the time to maturity and some dependent variables like the price of the option, I'm just going to call this a regression problem and feed it into my best ever regressor, which could be a kernel machine, random forest, deep neural network, depending on exactly what decade you learned about machine learning in. And then you got a model to predict the price of your option. So the machine learning researchers, when they do this, they would claim that their model does the same thing as the economist's really smart formula. It inputs these parameters and it predicts what's a good price to sell an option at. And they would claim that this is actually better because there's a smaller difference between the predicted price and the market price when you use these kind of models than the kind of formulas that economists come up with. So this is the background of when we started looking into this problem. So we can ask some questions about this. Do these models do what we really think they are doing? Should we really trust them? And how can we analyze these models to find out, what if they are going wrong? If so, how we can dehorse the model, how we can make a better model that we can trust more. So these are some of the things that we will go through now for this problem. So now we need to start with a little bit more detailed background in finance. Again, apologies, but there's going to be some symbols. So we need a symbol for the strike price. This is how much you will be able to execute the option at in the future. The underlying price of the asset at the beginning, ST. The moneyness is the ratio between those. The future date is like how far when in the future is the option going to be executed. And the time to maturity is like the difference between the current time and the future date. And ST is one of the big unknowns, which is what the price of the asset will be in the future. Right? So these are some of the symbols. Now, what the machine learning guy would do is say, okay, I observe some actually traded option prices. I observe all of these inputs for the prices, like the strike price, the time to maturity, and I train a regression model like this that inputs those and outputs an estimated price. And we want this estimated price to be similar to true market prices, right? So, but the economists will tell you that the right way to think about this kind of problem, rather than just training a totally black box model, has a particular structure. And this particular structure has looks like this, which I will try to demystify now. So there's two terms here. The integral term is going to be the expected value of the option at time t. So this big T is the future. So this should be discounted according to the fact that you are going into the future and there's some risk-free interest rate that you need to do to get the value of the option now, given its value in the future. Right? So that's why there's the exponent at the beginning. And then the reason the integral term is the expected value of the option in the future, there's this lovely term here which says that the value of the option is the difference between the strike price and the market price of the asset in the future. And so this is because of what you do with the options, right? If your strike price is lower than the asset price, you execute the option, buy the stock, sell it again, and you profit the difference, right? So that's why there's this difference in terms of the value of the option. And the max is to say if the value of the asset is too low in the future, you don't execute the option at all, right? So you're not going to lose money for it. That's why there's a kind of floor on that value of the option. And then the other part of this is the probability density of the asset price in the future. And so this is like the right way to think about these kind of things for various reasons, which I am not going to go into, but one of the reasons is that it prevents against various kinds of arbitrage, which you don't want the model to be able to allow predictions that can enable that. Okay, so why do we need these kind of nice, smart, rational option pricing models, which I showed above? Well, the simple machine learning solution of just training a regressor to minimize the difference between those seems like it could do a similar job with less annoying symbols. Well, one thing is we want to explain the behavior of the market and not just predict it. Other thing is the pricing problem is interrelated with other things that are happening in finance and other prediction tasks that we want to do. And other thing is that some trading strategies depend on rational predictions. And I will tell a bit about what that means now. So one particular example, which I will zoom in a little bit, of what can go wrong if you don't have the right kind of model for this, is that recall the kind of overall right way to think about it equation which I showed at the beginning. The second derivative of this equation with respect to the strike price becomes equal to the distribution over the asset price in the future, right? So that's just a kind of normative thing that you can get from looking at the right way to think about the problem. And so what that means is that whatever model you come up with for this, whether it's a decision tree or a neural network or a kernel machine, you would like it to have the property that the model's second derivative is equal to the distribution over future asset prices if you want some kind of guarantee that your model is doing something sensible. And so this is not something which holds for arbitrary regression models. This is quite a tricky thing to enforce for some kind of machine learning model that you come up with. So this is a graph of this distribution of asset price in the future for some perhaps good regression model, but not sane regression model. And so we get this thing where there are some probabilities that are negative, right? So it's implying a distribution. If you take the second derivative of the model and see what distribution it's implying, there's some negative value. So this is not a real probability. And it doesn't integrate to 1. And so that means all of the downstream trading strategies that you need that require this to be a probability distribution in order to examine its variance and skew and things like that are going to be broken, right? So this is kind of an example to show that an arbitrary model is not necessarily sane and it can't be, isn't useful for trading. Okay, so there's actually 6 sanity checks that we came up with that you want to enforce to make sure that your model is doing something sane, which I will go through briefly. And the machine learning guys are hoping that the model learns these sanity checks automatically from observing the sane data in the market, but it doesn't. Okay, so the first sanity check is, in English, what I call the asset price CDF constraint. So the second derivative of the model with respect to the strike price, if you do the kind of look at the normative equation at the beginning, you'll see that that derivative gives you a CDF of the future asset price. And so that means that it has a constrained maximum, because the CDF can't go greater than 1. Second constraint is the one we looked at before, the asset price distribution constraint. The second derivative of the model is the probability distribution of the asset price in future. The third constraint is that if you want an option with a longer time to maturity, there's a greater chance that the market value turns the wrong way. So the further in the future you want to hedge, the more chance there is for something to go wrong, and so the more expensive the option should be. So the prediction of the model should go in one direction with one of its input parameters. Another constraint, the one I call useless option has no value, is that if the strike price is very large, so you're never going to make money with the option because you can't do the whole execute the option, buy the stock, sell it again, because you're never going to make money if the strike price is infinite, then the price of the option is 0, because you can't use it to make any money. Another one is what I call in English market price for trivial option. So if the option has 0 maturity date, so you want to execute, it's an option who's supposed to be executed now rather than at some point in the future, then its value should be pinned to the difference between the current asset price and the strike price, because this is exactly the amount of profit that you can make from executing the option today. And final constraint is some boundary conditions to disallow arbitrage. So if you do things like allow the option price to be greater than the underlying asset price, then it opens some strange opportunities for arbitrage that you don't want to happen. Okay, so this is 6 constraints we came up with to define what does a sane model mean in our domain. How can we come up with a smart machine learning model that predicts the option prices really accurately but meets all of those constraints? And it turns out that in that most black of black box models of neural networks, they're actually one of the easier models to enforce these kind of constraints. So I'll tell you a little bit about the model we came up with that enforces these. So it's a two-sided neural network that takes the moneyness on one side and the time to maturity on the other side, and goes through some nodes and then eventually comes up with a prediction for the option price. And so specifically, the formula for this, I will try to demystify it slightly. So the two inputs are M, the moneyness, and T, the time to maturity. And then we multiply it with some weights, put it through some activation functions, and do some summing up, and we get the price. So the smart parts here are two things. One is that by exponentiating the weights here and here, and then adding it with a plus here and a minus here, we can enforce that all of the weights in one branch of the network are positive, and all of the weights in the other branch of the network are negative. And so by being able to enforce entirely positive weights in some part of the network or entirely negative weights in another part of the network is a useful tool to make sure the network is doing what you expect it to do, rather than something totally unexpected. And the other thing which is going to be important is the particular choice of activation functions. So one of them is soft plus activation, and the other is sigmoid activation. So if you define your neural network in exactly this way, with these positive and negative weights in this particular choice of activation functions, you can go through some lovely math and do some derivatives, and you will find out that you can actually enforce 4 of these constraints with this specially designed neural network. So you have the CDF constraint, the PDF constraint, the options get more expensive in the far future constraint, and the useless option constraint through careful choice of activation functions and weights. So we are halfway there. The other constraint that we mentioned was this trivial option constraint. So this is the one where if the time equals 0, so it's an option that's being sold to be executed immediately, then you want the value of the option to be exactly the difference between the strike price and the asset price. So we couldn't figure out any way to enforce this by design of the neural network. So what we did is we invent synthetic data. So we come up with synthetic options where for every synthetic option, the time is 0. So it's an option that's to be executed now. And then we make up different strike prices and different underlying asset prices. And then the value of the option is the difference between those two. So you can like pin the network's behavior at some kind of edge condition like this by synthesizing data for that edge condition, even though that's not data that will ever happen in the real world, because maybe nobody's selling this kind of options for executing immediately, because it doesn't make sense to sell that in the real world. But you can synthesize the data to say what that edge case should be. And similarly, you can synthesize data for the no arbitrage boundary conditions issue. So all of this is pretty good. We now have a model which meets all 6 constraints, and everything should be great. But it turned out that despite the fact that we meet all of the constraints now, the mean squared error is not good enough to kind of impress everybody with how accurately we can price the options. And in this case, it was more or less because the model was too simple. So this was quite a small neural network designed to be as easy as possible to meet all of the constraints, but not expressive enough to really model all of the different behaviors of the market. So actually what happens is you get these phase shifts. So if it's like deep out, they have all of these lovely jargons in finance, like deep out of money, and they mean things like, you know, if it's a far future option or a near to be executed option, or if the strike price is really different from the asset price, then like the pricing that you want kind of varies discontinuously as you get into these domains. So yeah, so we want to come up with a more expressive model to account for all of these different phases of behavior. And so we built a slightly more complicated neural network for this, which is a little bit like a mixture of experts, if you were around when people talked about those things in the 80s or whatever. So more or less on the left side here, there's a whole bunch of those single models that we talked about before. And they're abstracted away with those dashed lines. And each of those dashed lines is like one single model that's going to be responsible for like one zone of the input space. And on the right side is a model switcher. So on the right side, you're working out like what zone of the input space is the right zone, and then activating the right single model according to that zone. So it's working a little bit like a decision tree in that sense, like switching in different models according to the zone of the input space, or a little bit like a mixture of experts. And so I won't go through all of the equations of that. But this model performs much better in terms of it's expressive enough to cover all of the different types of pricing that you need, and gives you good MSE. So now the question is, can we enforce all of those constraints of sanity on this more complicated model? And that turned out to be a bit harder, but it turns out you can do all of the right derivatives and all of the right synthetic data to enforce 5 of the 6 constraints we talked about before. But the outstanding tricky constraint for the more complicated model is this asset price distribution constraint, which is that the second derivative of the model with respect to the strike price is supposed to be greater than 0. So to solve this one, we borrowed another old trick called learning from hints trick. And basically what happens here is we synthesize data where so for example, you synthesize data, and you have like a particular moneyness, which is like related to the strike price, and then you perturb it slightly. So you add a small number to it. And then what you say is, when you have 2 different inputs like this, one option with a particular moneyness and another with a slightly perturbed price, then you want the ratio, you want those things to have the right ordering between each other. And so since this is a second derivative constraint, we want the first derivatives to have the right ordering, right? So we can get the first derivative of the network, and then we can add a loss to say that particular option should have the right ordering of those first derivatives. And so when you add all of that up with all of the synthetic data, you are basically pushing the entire thing to a monotonically increasing function, or pushing the derivative to be monotonically increasing, so the second derivative is larger than 0. Right? So the point here is not necessarily that you know all of those details, but the point here is there are a lot of cool tricks that you can use to help you enforce that your network is doing something sensible that you want it to do. Okay, so we did some evaluation of this, of course. One of the biggest evaluations to date, all of the options from 5,000 trading days of S&P 500. And you can produce some nice graphs like this that show the pricing accuracy of different models in different quarters. And the one we came up with has the best accuracy going along the bottom there. And things go a little bit haywire during times like the financial crisis, which we were asking about earlier. Here's your reference to that. And if you add it all up, then the smart model we came up with has the best prediction accuracy. But this is not the part that we care about. The part that we care about is the sanity part, right? So let's look at that. So the sanity part, one of the sanity parts that we are particularly interested in is that the model is like internally representing this probability distribution over the asset price, right? And so for this to be valid and sane, this implicit probability distribution needs to be non-negative and to integrate to 1 and should have other like economically reasonable properties. So some previous guys have defined neural networks to do this task that may have good prediction errors, but the neural networks do strange things. For example, this is a PDF of the predicted asset price. So that's the x-axis here, and the probability of that asset price. So this is a neural network who's putting a lot of probability on the outcome that in 5 days the value of the S&P 500 will be 0, right? So this is something which might be concludable from the data, but you never really had any data around that edge case anyway. And because you don't enforce the edge cases of the neural network training like what we did, you can come up with things like that which don't make sense. And these guys don't integrate to 1, so you can't do all of the trading strategies that rely on these things being valid probability distributions. This is a few variants of our model with and without the different constraints. So without any of the constraints, you can have both of these problems, that you have negative probabilities here, and you have significant probability of a 0 asset price in a few days, because it doesn't go to 0 at the end here, right? But then if you add in all of the different constraints, you can eventually get to a nice, reasonable model that integrates to 1 and doesn't give significant probabilities to 0 asset price in a few days. Right? So, yeah, that's the kind of part of the results that we are interested in. Okay, so in summary, we can build a high-accuracy neural network that, besides being high accuracy, moreover, draws conclusions in the way that we wanted to draw conclusions. Via, in some sense, a meaningful internal representation. And it can make predictions with certain sanity guarantees, which vanilla neural networks can't. It's interesting to note that this was not an overfitting issue. The test MSE was good before we started. It actually gets better because the constraints that we give it are a little bit like inductive bias. But that's not the important part. Other thing is that this was an intrinsic horse infestation. It wasn't one of those infestations due to like the music was all regulated by the ballroom committee to have a certain tempo. You can take all of the option contracts on the entire market and train the model, and you will still get this horse. It's more to do with the unconstrained versus constrained way of training a network. It's not a data set problem. And so useful tips that might be relevant for you outside of finance problems. The neural net model doesn't have to be black box if you think about it carefully enough. Okay, this is a little bit harder to do in vision and audio than what we did here, but if you have some semantic inputs, you can think about your neural network hard, and maybe it becomes merely gray rather than black. And to do this, some of the tricks we used are things like careful modulating weights, activation functions, and when, and if necessary, synthesizing pseudo-data. Yeah, so the types of constraints that we talked about are things like pinning corners. And it can be very important to pin corners, actually, to make the whole prediction surface of the network do something sensible. So pinning corners and constraining how the model uses certain inputs. So like if the model's prediction has to be monotonic in one direction or other with an input, you can try to enforce how it uses the input in that way. And collections of these constraints can have qualitative impacts. So it's a combination of these constraints which give you things like internally representing a PDF somewhere. So yeah. Okay, so I guess some general discussion points related to today's points for discussion. How do we know if a model is sufficiently sane? Okay, so in this case, we are saying that if you think hard about your domain, you can get some requirements. So maybe the model should be invariant to tempo or whatever if it's music, or in our case, it should be monotonic in a certain direction with an input. With the caveat that necessary conditions for sanity are not quite the same as sufficient conditions for sanity. So we are kind of guaranteeing that our model here is not insane in a certain set of ways, but we are not guaranteeing that it's completely sane in every way. But at least we can make steps towards sanity. And yeah, this is an example of when a horse is not just overfitting, because we went overfitting before and we are still not overfitting. It's more subtle than that. It's about arriving at the conclusion in the way that you wanted to get there. And that way that you wanted to get there can be important if you have some downstream application, which in our case is trading strategies that depend on it having arrived at the conclusion in a right way. And yeah, important to avoid horses when you want to understand rather than just predict. And how can we make it robust to horses? Yeah, have to think carefully about your domain, think carefully about your model, and engineer your model appropriately. And yeah, thank you.